Last time we discussed differentials. The differential of something like dy is equal to f prime of x dx, where now we're thinking of dx as a small change, like an error in a calculation. This is not an infinitesimal number, it's a small perturbation or error, small error or perturbation, and then that results in a change or an error or a perturbation in y. And the amount, the scale, the difference in scale from a change in x to a change in y, if y depends on x, is the derivative. Okay, and we use this to for things like linearization, linearized approximations and approximation. Okay, so this is going to lead us into, so now we're in chapter 4. And chapter 4 is all about other applications, so more applications of calculus. Applications of calculus, in particular derivatives, applications of derivatives. What are the kinds of things we can do now that we have the power of derivatives with which to do that? So let's motivate what we want to talk about with a little example. So here's a function. How about this function? 10x times 1 minus natural log of x on the interval 1 to e squared, apparently. Okay, there's a function, and I would like to know something about its maximum value, max min value on this domain. Okay, I have no idea what this function looks like. I purposely chose one that's like, this is not something that would be reasonable to ask you to graph yet, right? So it goes from 1 to e squared, and it does something. I have no idea what. And I want to know about its maximum values or minimum values. How are we supposed to figure any of this out? Well, first of all, we can get a couple of endpoints. So what is the value of f of 1? F of 1, natural log of 1, 0. So I get a 1 minus, yeah, okay, fine, doesn't matter. Actually, I do want a 2. I want to put a 2 here. I had a 2 in my notes, and there's a slightly good reason for that too. Natural log of 1 is 0, so I get 2. 2 minus 0 is 2. 10 times 1 times 2 is 20. Okay, so this point, oh boy, this point is 20. Okay, how about f of e squared? How about the other endpoint? So we have one endpoint, let's get another endpoint. If x is equal to e squared, and you'll see in a second why I wanted a 2 there, what's natural log of e squared? 2, right? To what power should you raise e to get e squared? You should raise it to the second power. So this is a 2. 2 minus 2 is 0, so that's why I wanted that 2 there, so that would be 0. Okay, so in fact, this comes all the way down like that to 0. Now, I don't know what else is going on. Maybe it's positive, maybe it's negative, maybe it's oscillating. How can we try to figure out what's happening in between? Does your intuition tell you anything about what might tell us if there's some kind of maximum or minimum? Maybe just go straight down, right? Maybe just go straight down and there is no maximum minimum. But if there was a maximum minimum, what we do know is that this function is certainly continuous and it's certainly differentiable because it's made up of functions that are continuous and differentiable, right? We know that f is continuous and we know that f prime exists. So we have some idea about what would happen if there was a place where the function turns around. That would happen if, Jenny, if the derivative is 0, right? For the function to turn around like this, because it's differentiable, it would have to happen when the derivative is 0, right? So to turn around, need to have f prime of, well, at some point, some constant c of c equals 0. So let's see if we can find such a point. Okay, so what is f prime of x? Let's differentiate this function. 10x. Now we're experts at differentiation. Chapter 3 was all about getting really good at differentiation. We're all experts on that. So this is 10 is a constant. Then I have a product rule. So I'll differentiate the x, leave the 2 minus log alone. That's a natural log. Plus, I'll leave the x alone, and I'll differentiate 2 minus natural log of x. The derivative of that is Sid. Yeah, exactly. The derivative of natural log is 1 over x. The 2's a constant, so its derivative is 0, and the minus sign gives us a minus 1 over x. Okay, and so this simplifies to what? I get a 20 log x. No, that's a 2 minus. It's bad if I can't read my own handwriting. It's a 2 minus natural log of x. So that's not a 20. Well, it is a 20. It's a 20. Actually, let's simplify inside of here first, because this x minus 1 over x simplifies to -1, and that's a 2 plus a -1. This whole thing is a 1 minus natural log of x, and that's being multiplied by 10. So I have a 10 times 1 minus natural log of x, and I want to know for what value is that equal to 0. So what value will make this quantity equal to 0? Well, multiplying it by 10 doesn't change anything. When is natural log equal to 1? At e raised to the 1 is the power that makes, so at x equals e, natural log of x, meaning natural log of e, is equal to 1, and so 1 minus 1 is 0. So over here at e, now e squared is what? E is like 2.7 something. So e squared is like a little, between 8 and 9. Let's call this 9-ish. Okay, over here is e. Well, I guess I have it. I guess I have it drawn here already. So this c is e at around 2.7 something, is a place where the derivative is indeed 0. And in fact, that's the only place. The only place where the function can turn around is at this one spot. So actually now we can really give a pretty honest graph. So here's a pretty honest graph of our function. We know that it starts at 1 at height 20. We know that it has a local maximum, as we'll discuss exactly what that means in a second. We know at e squared, it goes down to 0. At e, what's the value of this thing at e? F of e. So I have 10 times e times 2 minus, what is the natural log of e? 1. So 2 minus 1. Oh, that's nice. So this is just 10e. 10e, e is 2.7, so 10e is like 27-ish. Okay, so here's 10e. Here's where the function starts, and it doesn't turn around anywhere else. And so without doing anything, just using our mind, we have given a rough sketch of what this function looks like. Does that make sense? Just by thinking about maximum and minimum values of functions on intervals. Should we check if this is close to accurate? Okay. Somebody is going to have to tell me 10x times 2 minus natural log x. I think I can remember that. Okay, 10x times 2 minus ln x. Okay, and I have to zoom out a little bit. So remember, we're not thinking about it in the whole domain. We only want the value from 1. I don't know how to restrict the range, but anyway, at 1, run is right here at 20. So here's 1 comma 20, and then it goes up, and then it comes down, and then it hits 0 at, I guess e squared is 7.3. I guess so. Okay, it is what it is. Doesn't quite make sense, does it? What's e? Isn't e 2.7, 27 squared? Oh, 27 squared, not okay, anyway. All right, so it's 7 something. So here's the graph. And that is basically the graph that we came up with our bare hands. Okay, that's the power of calculus. Dan. Okay, very good. How did we know that it was a maximum and not some other value? Well, we know what its value is. Its value is 27. which is bigger than 20.
How did you know to use E?
Oh, how did I know to use E? So in order for the function, because it's continuous, so we're going to prove this. So right now we're just using our intuition. We're going to actually prove these facts. We said if the function is going to turn around, in other words, if it's not just going to drop straight from 1, we know that at 1 it's greater than it is at E squared. At 1 it's at height 20. It has to come down to 0 by E squared. So maybe it just goes straight there. Or maybe it dips below and comes back up. Or maybe it goes up and comes back down. Or maybe it does a whole crazy wiggle thing before it gets there. Somehow it has to get there, and it's continuous and it's differentiable. So for it to turn around, for it to be going increasing and then turn around to decreasing, at some point the slope has to go from positive to negative, which means it has to cross through 0. So that's why we said, let's look for a place where the derivative is equal to 0. And we've computed what the derivative was, which was 10 times 1 minus natural log. How can that be 0? Natural log has to be 1. Natural log is 1 when x is equal to E. So that's how we knew to look at E. Very good question. Other questions? Okay. So let's look at this. Let's get some. This was all just kind of using our intuition and discussing colloquially, but let's get some definitions on the board. So what do we actually mean by a maximum or a minimum or a local maximum? So what would you call this point? A maximum, a minimum, a local minimum? This point right here. None of the above? You wouldn't call it a local minimum? Okay, fine. Let's go to this point. What would you call this point? That's a max, right? It's definitely a max, and it's sort of, not only is it a max over the entire domain, it's a max. I mean, not only is it a max kind of in its own little neighborhood, it's a absolute max, a global max. How about this point? Absolute min or global min? Yeah. This point, some people would say is a local minimum. Holland doesn't like that. There's actually some debate about this, so we have to. I'm actually with you, but we have to go by the book, because just somebody has to make somebody has to make a decision. The decision that I would make is not the same one as the one that the book would make, but that's what you will be tested on. This is the distinction between human mathematics and sort of mathematics. Mathematics is sort of well, the definitions are still made by humans, but they're the natural, the obvious ones. And sometimes there are non-obvious places where we have to make a choice, and then different people might make different choices. We'll get to that in a second. So this is what would be called a local minimum. So let's get all of these definitions straightened out. All right. Let me try to write a little bigger. Let me not try to sneak this into this page. New page. Okay. So what do we actually mean? Definition. Let f be a function. F is some function. Be a function on some domain. Domain D. Okay. So again, the picture I always have in mind, there's some domain D. I don't know, maybe it's open, maybe it's closed, whatever it is. And we have a function f that's on the domain. I never said that the function was continuous. I never said the function was differentiable. Okay, it is whatever it is. So f is a function on a domain. We say that C in the domain is a global, an absolute. Some people say global. So if you hear me say global, I mean the same thing as absolute. Maximum. If so in this picture, I guess right around here would be C. If what? If all other values of x give you a smaller value of f than C does. If for all x in the domain, the value of f at C is at least as large as the value of f at x. Does that make sense? Do you remember this thing? This means for all. All right. So that's what it means to be an absolute max. What does it mean to if we have an absolute min? So let's give this. Let me not use the same letter C. Let me call this, I don't know, A. We say that A in the domain is an absolute min or global minimum minimum if Nimmer. Beautiful. Okay, it's just the obvious thing. F of, I guess I called it A. F of A. Okay, if it's the smallest guy. Now this kind of has a problem. So let me fill that in. Okay, now it's a global min. What would a local max or min mean? I didn't really make one on this picture, did I? Here we go. There we go. So why is this point, can I still call it C? You know that it's not the same C as that C. Why is this point a local max in this picture? Right. Please. Thank you very much. Oops. Yes, thank you. If the value of f at A is smaller than the value, or no bigger than the value of f at any other point, that's an absolute minimum. Okay, so that's an absolute minimum. Global, absolute or global minimum, absolute or global maximum. How about local max or min? We say that C in the domain is a local max if, so I don't want to look at the whole domain. I want to look at some interval around C. If I restrict my attention to, if I zoom in just to this little range, on this little range, C is the maximum value. Okay, so if there exists an open interval, let's say I, an open interval, and that open interval should contain C, of course. C is in I. Okay, so I is this open interval. Open means that I have round parentheses. We say that C is a local maximum if there's an open interval containing C, such that on this interval it's a maximum. So in other words, for all values of x in the interval. Now the interval might not necessarily, like the interval could not necessarily intersect with the domain. So let's make sure we're only plugging in things from the domain. So this is the intersection of I. This means that x is in I and x is in the domain. So we can apply the function. We say that C is a local maximum if there exists an interval, so that when we localize to that interval, in other words, we only consider the function, the points x in the domain that are in the interval also, then f of C is at least as large as f of x. Does that definition make sense? So in other words, if we restrict our attention not to the whole domain, but just to this interval I, then in this interval, there might be larger points, larger values of f outside of this interval, but at least in this interval, C is the dominant point. So funny things happen with closed intervals, and I'll try to illustrate why I want this interval to be open. Let me save that question for just a 5 minutes. Tell me your name again. Alyssa. ST, such that. ST is such that. Sorry. ST is such that. Okay. Should I write down the definition of a local min? Or can I do ... local min ... inequality goes the other way. Okay. Do I have a local min here? I guess, well, A is a right here, this point. Well, I have to give it a value. So right here, this endpoint, and I have to let it be in the domain. This endpoint is also a local min, because if I take an interval around it, all of the values in the domain near it will be larger. Okay, so it's the smallest point in a little neighborhood, in its own little neighborhood. Okay, does that make sense? So hold on, this is where some people would argue whether it really is a local min or not, because you don't have an open interval in the domain. It's not an interior point of the domain. Your book says, yes, let's call that a local min. So this is a local min. Local min. This is it's also a local, but it's an absolute max, min rather, absolute and local min. This is a global max or absolute max. Oh, and some people call local relative min. Local is the same thing as relative max or min. So let's call this a relative max. Relative max. Okay, does that make sense? This stuff is just too simple? We're spending a lot of time talking about obvious things? Yes, okay. I mean, we also have some math notation, so I want to make sure that's not confusing anybody. We've used it before, but maybe it's been a minute since we used it. Everybody knows what we're doing. All right, let's prove some theorems about these things. Let me give you a couple more examples. So here's an example. Function f, which is defined to be, let's say, x on 0 to 1, and then 0 when x is equal to 1. So its domain, the domain of the function is the closed interval 0, 1. Tell me, take 2 minutes and tell me its absolute max and min, and its local max and min. Okay, take 2 minutes, figure this out, and tell me what you find. And give me a thumbs up when you got it. What's the first thing you can do with this one? The other one we couldn't graph, it was too complicated. Although eventually we did graph it and it wasn't that complicated after. This one, you can just graph it, right? Draw a picture. Zane, where's your pen? Oh no, can you borrow some paper from somebody? I guess not borrow, you're not gonna give it back. But is that a 6 or a 0? Is that a 6 or a 0? That is meant to be a 0, thank you. Anybody got it yet? Will, where's your paper? Might help. Anybody got it? What's the picture of this look like? Anybody draw a picture? What'd you get, Yusuf?
14 closed circle.
Okay.
1, 1 open.
1, 1 open. Yeah. Right. This is not a hard picture to draw. I hope you'll agree. Okay, so where's the local min? Do you have any local mins? Let's think back to the definition. Are there some, okay, how about absolute mins? Are there some numbers that are just like some places where the function is just the smallest it's going to get on the entire domain? Right. At 0, so 0 is an absolute min. I agree. If you're an absolute min, you're automatically also a local min. Absolute min means you're the smallest on everything, and local min means you're the smallest on a sub region. Right? So absolute min and hence local min. And that's it. No other minimum values. Annabelle, did you get a minimum value? There are 2. Yeah, there's another place where it takes the same value. Both of these are absolute minimum. Okay. Both of these places are places where the function takes the smallest value it ever will. that make sense? How about max? Tell me your name again. Yeah, you shook your head. Drew. So 1-1 is a good guess. 1-1 is a good guess for where a max would be, except that there is no place. Remember, what does it mean to be a max? It's a value C, so that for every other value, there's something bigger, Sid. Well, so this is why we use in some places open brackets, in some places closed brackets. This has no maximum. There's something called a supremum. It has a supremum. Supremum and infimum. I'm not even sure we're going to talk about supremum and infimum in this course. It's a more delicate topic. So it does not have a maximum. The distinction between a maximum value and a supremum is that a supremum is a limit of potential maximum values. That's one way to think about it. This is not a max. There's no value C so that f of C is greater than f of x for all x, even in a neighborhood. For all x. Because no matter how close I get to 1, there are still numbers that are even closer to 1 that have a larger value. So there is no local maximum. So no local max and no local min. Okay, Raga. So that's what a supremum, the supremal value of the function is a limit of all upper bounds. Let's not go into this is about is there some value C where the function attains the largest value it possibly can? And in this case, the answer is no. There is no place, there is no location C. This place 1 is the point where you would think it would get to its maximum, but right there it gets cut off by this discontinuity. Annabelle, and then Peter. There exists. The E is a there exists. This means there exists. There exists. The I is just the name of an interval, like A to B or something. There exists some interval I in the domain. Does that make sense, Peter?
You said there's no local max for load, but
I'm sorry, there's no local max. There's no local or global max. That's what I meant to say. There is a min. There's a local min and an absolute min and a global min. Yeah, there are two values. Nobody said that there has to be a unique absolute maximum or minimum. There can be more than one absolute maximum minimum, or there can be none, as in the case of the maximum value. Okay, does that make sense? Alyssa. If the interval was closed bracket 0, open bracket 1. Okay, great question. Okay, so let's do another example. This is Alyssa's example. F of x is just equal to x on the interval x to 1. No discontinuity. Does this have a max in the domain? Yusuf says no. Zain says no. Tell me again. Naeem says no. Why? Why Naeem? Right. There's no place, there's no one location that I can stand at and be taller than everybody else. I can't stand at 1 because 1 isn't in the domain. Okay, does that make sense? So this has also no max. No local max, no global max. Okay, let's state, we're not going to prove, unfortunately, something called the extremal value theorem. Extreme value theorem. It's a very important theorem. It says that if you have a continuous function, if f is continuous on a closed interval, what's important here is that the interval is closed, A to B. Unlike this interval, exactly as in your question, Alyssa, unlike this interval, which is half closed, but also half open. if f is continuous on a closed interval, then f does have a max, an absolute max and min. There is no way to draw a continuous function on a closed interval a and b and have it not go through a maximum value and a minimum value, wherever those might be. It might be in the interior, it might be at the endpoints, but it has to go through. This theorem, which is blatantly obvious if you look at it, is actually surprisingly difficult to prove, because what goes into a rigorous proof is the very nature, the fabric of the real numbers, which is something we're not covering in this course. Right. Y is equal to 5. Yeah, a constant function. Okay, so here's a constant function. So every point is a maximum and every point is a minimum. Yeah, that's a perfectly valid example. Yeah, every point is an absolute maximum and an absolute minimum and a local maximum and a local minimum. Sid. Sure. Yeah, all of the points, all of the values from 2 to 7 are all maxes if this function takes the value. They're all absolute maxes, they're all local maxes, they're all local mins, and they're all absolute mins. Yeah. Okay. A function can have a function that's not constant can also have, if you have a function that's continuous, maybe you have something like this. Okay, all of these points are absolute maxes and local maxes for the function. These are all absolute and local maxes. Does that make sense? All right, so we're not proving this theorem. This theorem is, as I said, it's shockingly too hard. Because to give a rigorous proof, again, we have to understand what the real numbers actually are, which we're not going to do. But there is something that we can prove, which is I like to call this the first derivative test theorem, first derivative theorem. Okay, this says the following: if you have a continuous function, if f is continuous on, let's say, a closed interval, a to b, and that function has a local maximum or minimum at an interior point, and f has, let's say, a local max at an interior point C, in the interior, meaning it's not equal to A or B. A and B are the extreme values of the interval. So if it has a local max or min, let's worry about the max version of the statement, but there's an equivalent statement for min. If f is continuous on a closed interval, okay, so I have a closed interval A to B, B, okay, and it has a local max. And let's say f prime of C, at this point C where it has this local max, exists. So if there is a derivative, if there's an existing derivative at that point, then that derivative must be 0. Exactly. We use this theorem, we didn't even, we use this theorem kind of in our minds in our previous example, but now we can actually rigorously prove it. I'm just saying, I don't know about, forget about global, because global could be, we'll discuss in a second about a general strategy for all kinds of maxes and mins. But right now, let's just think about a local max, for example, okay? So if we have a continuous function on a closed interval, and let's say it has a local maximum at an interior point, okay? So there's an interval, an open interval around which the function has is the largest value that any other value takes. Okay, so if the derivative exists at that point, then the derivative has to be 0. Now the derivative doesn't have to exist. The function could be continuous, and it could have, something like this, where the derivative doesn't exist. Then I have nothing to say, because we're assuming that the derivative does exist. If the derivative exists, we want to prove that the derivative must be actually 0. Okay, so let's prove this. The proof is not hard. This is a little bit of a flavor. Again, this is not a course in proofs, but I still want you to understand what proofs look like, so that when you get to higher level math classes. So I think in 311 you can actually prove the extreme value theorem. Maybe 411. This is one that we can prove right now, because the proof isn't hard. Okay, so let's think about what it means for f prime of c to exist. That means that the limit as x goes to c of f of x minus f of c over, should I not call it x? You guys get confused when I call these x. Let's call this u. U minus c, this exists. And what does it mean for a limit to exist? It means that the limit from the left exists and agrees with the limit from the right. Right? Now, C is a local max. C is a local max. So for all u nearby C, near C, in other words, in some neighborhood around C, there's an interval, so that if we restrict ourselves to that neighborhood, for all u near C, f of C is going to be larger than f of u. Okay, so let's think about this limit from, let's think about the limit from below. Let's look at the limit from below of f of u minus f of c over u minus c. What do we know about the numerator? It's the limit as u goes to c. What's happening to the numerator? Is it positive? Is it negative? It's not necessarily negative, but it's non-positive. So the numerator is less than or equal to 0. Because f of c, we said f of c, for all things close to c, like things approaching c, f of u is going to be the smaller value. So f of u minus f of c is going to be negative. How about the denominator? We're approaching c from below, so u minus c positive or negative? U is smaller than c, so if I take u minus c, guys, anybody here? If I take something smaller and I subtract something bigger, then I get something negative, yes, right? If I take the ratio of two negative things, the two negative things are positive. The ratio of negative things is positive, and so every possible value of this quotient is non-negative. Every possible value of this quotient is non-negative when u goes to c from below. Well, that means in the limit, if every quotient is non-negative, then the limit, in other words, the derivative, has to be also non-negative. Right? You can't all of a sudden skip to a negative value if all of the values nearby were non-negative. Does that make sense? What about the limit from below? From above. Now let's look at the limit from above. Look at the limit as u goes to c from above of this same expression. What do I know about the numerator? The numerator, we still have a local maximum. So whether you're above c or below c, the value of f of u is going to be smaller than the value of f at c. F of c is the king of the hill. So f of u minus f of c is negative, or at least non-positive. And how about the denominator? U is bigger than c, so u minus c is positive. So the whole fraction is negative. So what happens if we take a limit of negative things? Can a limit of negative things ever come out positive? No. So that tells us that f prime of c cannot be positive. So for two different reasons, f prime of c is non-negative. It's also non-positive. There's only one number that's non-positive and non-negative. 0. Okay, therefore f prime of c is 0. So that's the kind of thing, that's what I mean by a rigorous, or at least quasi-rigorous mathematical proof. So that's the first derivative theorem. If you have a continuous function with a local max, the same argument applies with a local min and the same proof, except you reverse who's positive and who's negative. And you have a local extremal point in the interior, because I need to be able to go below and I need to be able to go above the value of c. I'm comparing those two intervals to one another. If you have an interior point c on which the derivative exists, then we just proved that that derivative must be 0. This is the kind of thing that at your age, I don't think I would have liked this theorem, because it's like, it's obvious. We know we've known this for weeks now. But here's a rigorous mathematical, quasi-rigorous at least, mathematical proof of it. All right. Yeah, and so the importance of these points is such that we give them a special name. So definition, we say if f prime of c is equal to 0, or if the derivative doesn't exist, or f prime does not exist, f prime of c does not exist, either because one of the one-sided limits doesn't exist, or because the two limits don't agree. There's all kinds of ways that a limit cannot exist. We say that c is a, does anybody know what these things are called? Am I hearing something, or is there a table being moved outside? What is it? Min or max is a good guess. It actually is not necessarily a min or max. Extremal is also a good guess. It's not necessarily extremal, as I'll show you in just a second. But it is a place where it's critical that you examine what's happening. Okay, I gave it away. Yeah, it's a critical point. Is a critical point for the function. Let me show you why it doesn't have to be a min or max. Let's look at the function y equals x cubed. What's the graph of y equals x cubed? Yeah, everybody knows. Just goes like this. What's the derivative of x cubed? 3x squared. Where is this equal to 0? At 0. So at 0, the tangent line is indeed horizontal, but it's neither a max nor a min, neither locally nor in an absolute sense. Okay, so it's not an extremal point necessarily. It's not necessarily a local max or min, but it's certainly a place where you better check if you're trying to understand the max or min structure of a function. Does that make sense? So in fact, let's turn that into an algorithm. So here's an algorithm, procedure. You know what an algorithm is. Algorithm, by which I mean a procedure for finding local and absolute maxes and mins. First of all, you better check the endpoints. Look at endpoints. Look at endpoints. You better look at the critical values, critical points, critical values. That is where f prime doesn't exist, or f prime does exist and is equal to 0. And if you have any discontinuities, or if the function is defined in some piecewise way, piecewise definitions, piecewise endpoints. So these are all the places you should look. Evaluate the function, evaluate f at these places, evaluate f at these places, and compare. Compare meaning, okay, now you know the only places where you have to look. Instead of needing to look on an entire interval, which as a human being you can't without graphing it on a calculator, on a computer or something. So without graphing it, you can zero in on exactly where you need to be looking to try to find maximum or minimum values. Okay. Do I have a nice example for us to mess with? Yeah. All right. Let's look at an example. Why don't you guys give me an example? I don't like my example. Give me a function. Let's get something not too crazy, but let's get a little crazy. Give me some piecewise, as x goes between what? -2 and 7. Go easy. 1. 7. It's fine. As x goes from 1 to 7, you want? All right. Give me some nice functions. Not too bad. Sine x. Okay, that's certainly doable. And what? Cosine, really? That's too vanilla. Come on, give me something. 1 over x squared. Fine. Fine. Okay. I'm not going to try to understand the maximum and minimal structure by graphing yet. First, we're going to apply the procedure. Okay. So let's collect the places to points of interest. Round up the usual suspects. Usual suspects. Usual suspects are, what are my suspects? -2, -2, 1, and 7 are certainly suspects. Where else? What's the other thing I have to look for? Those are the endpoints. So -2 and 7 are the endpoints. 1 is a place where there's a discontinuity, like a piecewise thing happening. So we've got those. What's that? 0. 0. Why 0? Because this isn't defined as 0. But actually 0 is not in the domain. So I'm not worried about that, but I do need to worry about the derivatives. So let's take the derivatives. F prime of x is equal to, derivative sign is cosine. This is, again, only on the interval -2 to 1. This is going to get interesting, actually. And the derivative of x to the -2 is -2 x to the -3 on the interval 1 to 7. Okay, so I have to worry about where this isn't defined, which is at 0. Why not? It's not in the domain. This is undefined at 0. Undefined at 0, but that's not in the domain. Not in domain. So I don't care. 0 is not in this piece of the domain. Okay, so there are no critical values from here. No critical values. No critical values. How about here? Now we have to think for a minute. All right, cosine. I'm going to resort to a picture. Cosine. So I know the cosine looks like this. I got to go to -2. Pi over 2 is pi is like 3. So pi over 2 is like 1.5. 1.5. So we're stopping at 1. 1 is over here somewhere. So there are no zeros. I'm not worried about any zeros there. There is one place, though, that I'm worried about zeros, because I'm going to go down to 2, -2. -2. This is pi. Pi is where I hit this -1. So negative pi, of course. That's -3. This is 1.5. 2 is right about here. -2 is right about there. There's -2. So there is a point where I do get a critical value. Okay, so what is the critical value? -pi/2. -pi/2. Okay, so that's one more usual suspect to round up. It's a place where the derivative is equal to 0. Where the derivative is equal to 0 or where the derivative doesn't exist. These are my usual suspects. So I've rounded up the locations that I need to worry about. Now I need to evaluate the function at these places. Okay, so f of -2 is equal to sine of -2. We'll need to figure out what that is. I don't know what that is. Then I need to worry about 1. At 1, the definition says I choose sine and not 1 over x squared. So it's sine of 1. F of 1 is sine of 1. Don't know what'll happen there. f of 7 is 1 over x squared, 1 over 7 squared, 1 over 49, 1 over 49. And finally, f of negative pi over 2. Negative pi over 2 means we're in the realm of sine. And what is sine of negative pi over 2? -1. -1. Okay. So now we can think about what this graph actually looks like. So we're going out to 1 with the sine function, and then down to -2 with the sine function. Sine starts at 0, so it's going to go up to something, whatever that sine of 1 is. It's going to go down to, it's going to go down past negative pi over 2. Negative pi over 2, where it achieves a value of -1. This is -1. And then it's going to come back up to wherever sine of -2 is. And then I skip from here to 1 over x squared. So I start with 1, which is a little bit higher than sine of 1. This is sine of 1. And then I go down like 1 over x squared. And I go down until I get to 7. And at 7, I'm at a height of 1 over 49. I mean, this height is 1 over 49. Okay. So now I can look to see what's going on with maxes and mins. Now, there's one more thing that I should have said, which is not just at the piecewise ends, you have to look at both sides. Both sides if something is piecewise. So I looked at f of 1, but what is f at 1 a little bit more than 1? So in other words, when I'm a little bit, where am I? Here. If I'm going, what's the limit? What's the limiting value of f as f approaches 1 from above? It would go to 1. Okay, so this would go to 1, and that's the picture we have here. All right, now that we have all those points, we can see which of those are maxes, mins, local maxes, local mins. So tell me which is which. You want to take a minute and think about it? This was sort of the hard part, but now I think we can, on our own, figure out the rest. So take a minute. Decide which of these values are local maxes, local mins, absolute maxes, absolute mins. At this point, I've basically given it to you once we have the picture. Who's got it? Wow. I've made a very simple concept seem very complicated, haven't I? You just look at it and say, yeah, I know what's what. So if you're overthinking it, try to just use your intuition about what these things should mean, and then tell me if you've got it. The definitions are meant to be a rigorous way to access your intuition. So try not to overthink it. Okay, can I have a thumbs up for who's got it? I still only see 6 thumbs up. 7. I mean, if you just look at the picture, what's this point? Local, but not global max. Okay, so that's at -2. This is a local max. How about this point? Absolute min. Absolute min. Not only is it the smallest in its neighborhood, it's the smallest overall. So that's at -pi/2. This is an absolute min. And of course, a local min, because any absolute min is automatically a local min. How about sine of 1? Absolute max? Local max? Local max means there's an open neighborhood around. And this is why we want open. Because if I took a closed neighborhood, I could take a closed neighborhood that includes this point at the end point, and then it would look like a max. But if I said open neighborhood that includes this point, An open neighborhood must include values to the left of it as well as to the right of it. And if we're going to the right, then it's not a max. There are larger values. Just a little bit to the right of it, there are larger values. So this point is nothing. Neither. Not max or min. Does that make sense? So this is where it's important to make the distinctions about the definitions, because the definition says, in other words, I want this one to be an interior point of an interval. Is it the interior point of an interval on which it's the largest, on which it's the king of the hill? And the answer is no. If I go a little bit, any little jiggle to the right, yes, you're left. Anyway, and I get larger values. Ying. That's right. We're not applying a theorem here. We do not have, that's right. In fact, this is a failure. This is one reason that continuity is essential in the proof of, which I didn't give, but in the proof of the extreme value theorem. We assume that the function is continuous. If it's not continuous, it need not have an absolute maximum or minimum. And this is an example of that. This is an example of a function which does not have an absolute maximum. Okay, how about this point? Local min, but not a global min. So this 149 is a local min. Now this is a supremum, but not a max, because there is no value at the top. Not a max. Not a max. And this is nothing. Okay, does that make sense? Again, you're going to have a bunch of homework problems. Hopefully you'll get more and more used to this as we do homework with it. Bless you. Okay, let's use this for a few more things. So here's something called, do you guys remember the intermediate value theorem? Intermediate value theorem. We had this a long time ago. What is it? What does it say? Intermediate value theorem. Yeah, if exactly. If a function is continuous on a closed interval a to b, so if I have a closed interval a to b, and here are my function values, f of a starts here, f of b ends wherever it does, f of b, okay, and it does whatever it does. If it's continuous, all I know about it is it's continuous, then for any value between f of a and f of b, then for all z in, let's say f of a is smaller than f of b, there exists, that value is hit somewhere. Might be hit more than once, doesn't matter, but there exists a c in the domain such that f of c is equal to z. Okay, we can always hit an intermediate value. Remember that? Let's prove a couple of theorems that are like this theorem. So one is that nobody really uses Rolle's. Well, that's not true. Rolle's theorem is important in and of itself, but it's a warm up to something called the mean value theorem as opposed to the intermediate value theorem. The mean value theorem is something like intermediate value theorem for derivatives. That's one way of thinking about it. Let's look at Rolle's theorem. Rolle's theorem says if you have a function that's continuous, if f is continuous on an interval a to b, and it's differentiable, f prime exists on the interior, on the open interval a to b, okay, so it's continuous and it's differentiable on the open interval, and let me assume that it starts and ends at the same point. Okay, so let's get a picture of that in our heads. Here's a, here's b. The function starts and ends at the same value. It's continuous, not just continuous, but differentiable. Here, I never said anything about differentiable. It could have all kinds of crazy behavior, and still the intermediate value theorem would apply. Here, I want to know that the derivative exists at every point in the interior. Then, if the values agree, then there exists some point, at least one, in a to b, such that the derivative is equal to 0. So if the function starts and ends at the same value, it can't do that without at some point turning around. That's exactly what we were, again, implicitly, our intuition was telling us. There's some place where the derivative not only exists because it exists everywhere, we assume it exists, but its value is exactly equal to 0. Okay. Anyway. Right. So the first derivative theorem said if it has an extreme value, the first derivative test theorem, that's a very good question. Where was it? I just missed it. It's right here. It's right here. If it has a local maximum, then at that local maximum, the derivative is equal to 0, assuming the derivative exists. Okay. If it has a local maximum, then the derivative exists. If it has a local maximum and the derivative exists, then the derivative is 0. This theorem, it's very, very good to compare these two. It's very important to compare these two. This theorem says, all I know is that the derivative exists, and I know that the start and end points are the same. Then there has to be some place where the derivative is 0. Okay. The derivative could be 0 without having a local max or min. Yeah, as we saw before, like with the function x cubed, the derivative is 0. So if you take that x cubed and you sort of, anyway, should I continue that? You know what I'm saying? That's right. I didn't say that this C was a local max or min necessarily, just that there is some place where the derivative is 0. Okay. Okay, how do we prove this? Let's look at the proof. Okay, so what we know, let's think about what we know. We have a continuous function on a closed interval. Continuous function on a closed interval by the extreme value theorem. We're going to combine. So f is continuous on a closed interval, a to b. By extreme value theorem, it has a absolute maximum and an absolute minimum. It has an absolute max and an absolute min. Okay. Now it could be that those absolute maxes and mins. So if that absolute max, max or min is at an interior point, C in A to B. So I don't know where the absolute, maybe the absolute max is at B itself. I mean, there's it could be that that we have something like this where the absolute max is at B. So if I have some max or min local that's an absolute max or min at an interior point, then so that would be something like this at an interior point C. Then this is also a local max or min, But now, as Nimmer said, now we can use the first derivative test. The first derivative theorem tells us that f prime of this point is equal to 0. The only other option is that the absolute max and min. So alternatively, the absolute max and min could both be at the boundary. In other words, x equals A and B. If I have an interior, I have an absolute max or min somewhere. I have an absolute max and an absolute min somewhere. If I have at least one of those in the interior, then I'm already guaranteed to have a point where the derivative is 0 by the first derivative test. If I don't have either of those in the interior, that means both the max and the min happen at the endpoints. But the endpoints are equal. So if the endpoints but f of A is equal to f of B. So if one is a max and the other is a min, or both are maxes and both are mins, they're both maxes and mins, that means the function is constant. But which implies f is constant. It can't go up or down. Well, if it's constant, then its derivative is 0 just because, which implies the derivative is 0 on the entire interval. So either way, we found points where the derivative is 0. Okay, does that make sense? Again, this is not a proofs course, so we need some. I'm not expecting you to be able to repeat arguments like this, but I would like you to have some familiarity with arguments like this and have some understanding of it. Let's use this to prove the really fundamental thing, which is the mean value theorem. Mean value theorem. I call this the EZPass theorem. When the EZPass was first being brought into the state, I don't know if you guys remember this, there was a big uproar. People didn't want to use it. Why not? You get out at exit 9, you get on at exit 9. There's a timestamp of when you come in, right? You get another timestamp when you arrive at the GW bridge or wherever you're going. It knows the distance. It knows the time that you traveled. What were people worried about? Speeding tickets. They were like, you're going to prove that I went over 65. Back then it was 55. Because the distance I've covered, my average speed, if the average speed is over 65, then of course there must be some place where I was going over 65. That's the mean value theorem. The mean value theorem. So eventually they said, no, I promise we're not handing the data over to the police. No one's getting a speeding ticket. Okay, fine. We're all using EZPasses now. The mean value theorem says, let f be continuous on a closed interval, AB, and differentiable, and f prime exists on the open interval A to B. But I'm not assuming that it's equal at the endpoints. So whatever the value is at A, here's another value at B. Here's f of A. Here's f of B. And I don't know what's going on in between. It's continuous and differentiable. Continuous and differentiable. I mean, differentiable implies continuous. Anyway. Then, so whatever your average speed over that time period is, there must exist some instantaneous place, some place where your instantaneous speed is the average. Then there exists some point C in the interior, some point C in the interior, such that what's your average speed over this interval? How far you went, f of B minus f of A, divided by how long it took you. B minus A, right? That's the average slope. So that the average slope is exactly equal to the instantaneous slope at some point. So what's the instantaneous slope? F prime of C. F prime of C. Okay, this is why the police will be sending you a speeding ticket. You must have been going 80 if you averaged 80. At some point you were going 80. Does that make sense? All right, let's prove it. The proof is very simple. We're going to make a new function. And in the interest of time, let me not belabor how you would cook up such a function, but it's a very simple function to think of once you think of it. So here's what I'm going to do. Okay, it looks a little complicated. I'm going to see how much progress I've made from f of A, and I'm going to change it by the slope, this average slope, times how much time has gone by. That's the intuition behind this function. But never mind, we just said, let's define this function. What is the value of this function at A? So I have f of A minus f of A, whoops, that's 0, minus this average slope, f of B minus f of A over B minus A, times A minus A. I'm setting x equal to A. So G of A is 0. How about G of B? G of B is f of B minus f of A right? F of x minus f of a, when x is b, minus this average slope, f of b minus f of a over b minus a, times x minus a when x is b. So this is b minus a. What happens to the b minus a on top and bottom? They cancel. And so now I just get f of b minus f of a minus f of b minus f of a. 0. So whatever this g function is, it starts and ends at 0. F was differentiable. All I did was add a linear term. So g is differentiable and continuous. We can apply Rolle's theorem. It has the same start and end point. By Rolle, there exists some c in the interior, a to b, so that g prime of c is equal to 0, right? G prime of c is equal to 0. G prime of c is the derivative, because g hasn't changed from when we went from a to b. Does everybody see that? But what is g prime of c? Let's compute g prime of c. G prime of c is equal to, or g prime of x. Let's compute g prime of x. G prime of x, what's the derivative of x? So that's f prime of x. F of a, what's the derivative of f of a with respect to x? What's a? A is a constant. A is not moving. So f of a is a constant also. So this is just 0. Okay, this is just 0 minus this constant f of b minus f of a over b minus a times, what's the derivative of x minus a? 1. And so that, when I set x equal to c, that is equal to 0. And so that is exactly the average slope being equal to the instantaneous slope at some point. So Rolle's theorem is very simple to prove, and it has this very nice and very important corollary, which is the mean value theorem. All right. Let's use this for one example, and then we got to go. Any questions on the mean value theorem, the statement? The proof, hopefully you followed. I mean, look back over it, but I'm not testing you on proofs. Is the statement clear? The EZPass theorem. Your average, whatever your average speed was, at some point you were instantaneously going that speed, unless you like have a hyperdrive and can jerk your speed non-differentiably. Okay, let's do one example, and then we got to go. Prove that I don't know, x cubed plus 3x plus 1 has a unique root. So it's a cubic. So I know it's going to start at negative infinity. I know it's going to end at positive infinity. It's got to go through 0 because it's continuous. But does it go through 0 once or more than once? Maybe it has like more roots than just one root. It could have 3 roots, I guess. Right? How many roots? So one root is by the intermediate value theorem. It's if I put x equals negative 100, this will be hugely negative. If I put x equals 100, it'll be hugely positive. One root we get from the intermediate value theorem. Now, can it turn around? If it wants to get another root, it's got to turn back around from 0. Can it hit 0 again? Well, if it hits 0 again, then by Rolle's theorem, there's some place where the derivative is 0. If there's another root, if there exists another root, then Rolle implies that there exists a place where the derivative is 0. If it hits 0 again, then somewhere in between it must have hit 0. But what is the derivative? F prime of x. What's the derivative of this function? 3x squared plus 3. You take a square of any number, you multiply it by 3, and you add 3, and you'll get something that is not just non-negative, but strictly positive. So this is never equal to 0. The derivative is never 0, which means the function can't turn back around. Once it hits 0 once, it has to just keep going. So not only does it not hit 0 more than once, it's always increasing. It's always strictly increasing. Okay, so it has a unique root. It has one root, and it can't have another by Rolle's theorem. All right,